So my name is Reinhard Heckel. I'm an assistant professor at the Technical University of Munich and an adjunct assistant professor at Rice University. So today I'm going to talk about measuring robustness in deep learning-based compressive sensing. So this is joint work with my student Mohammed, who really did most of the simulations that I'm going to talk about, and Akshay, who is an assistant professor at Stanford University. So the problem we are going to consider in this talk is accelerated magnetic resonance imaging. So the problem is as follows. Our goal is to image some part of our body. So in this case, a knee, but we are only collecting undersampled data of this knee. So the scanner only collects in our setup 4 times undersampled data. So the white lines here correspond to the data that we collect. The black lines is data that we do not collect. And our goal is to estimate the original image from this undersampled data. So that's an ill-posed inverse problem, and in general we cannot reconstruct our image unless we make some prior assumptions on the image. And those prior assumptions on the image are traditionally sparsity based. So the traditional approach to this problem is to assume that our image is sparse in some basis. For example, the gradient could be sparse, in which case we impose a total variation norm. In this case, the total variation norm would be small, and therefore recovery could be accomplished by solving this convex optimization problem. So note that this approach to signal recovery is not based on learning at all, right? So the prior that we impose is handcrafted, and the only parameter that we learn here is the lambda parameter, the regularization parameter. That parameter is typically learned because it's chosen based on training data. But other than that, that is a non-learning based approach. What has happened in the past few years is that learning-based approaches have become extremely popular, and the perhaps most successful approach is to train a neural network end-to-end to perform signal recovery. So what people have been doing is they designed very particular networks, variants of convolutional networks that take the measurement and map the measurement to a clean image. And this has shown really good performance, as we will see later. Now we have seen 2 approaches. So here's a third approach to signal recovery, and that's based on untrained neural networks. So that's something me and my group have been working on a lot. So here the idea is to assume that an image lies in the range of some untrained neural network D, and then we optimize over the range by optimizing over theta of this untrained neural network. So in this case, we impose the prior assumption that our image lies in the range of this untrained neural network. And that's conceptually similar to a 1 minimization in the sense that we also have a handcrafted image prior. Just in this case, the handcrafted image prior is that our image lies in an untrained neural network and not that it's sparse necessarily in some basis. Okay, so now the question is, well, how do these methods perform relative to each other? So we have seen like 3 conceptually different methods. And one data set to evaluate them on is the fast MRI data set. So the fast MRI data set is a large collection of images and corresponding measurements on which MRI reconstruction problems can be evaluated. Okay, and so if we look at these 3 different methods and we evaluate the image quality based on this data set, then we find that sparsity-based methods really just work okay. So what you can see here is there are visible artifacts. The untrained neural networks, for example, the deep decoder that we just saw, works pretty well. So what you can see here, there are at least no artifacts. But if we look very closely, it turns out that the end-to-end neural networks like a UNet or a variational network, they work like really well. So the challenge was, so the fast MRI challenge was competition, right? And that was won by these end-to-end neural networks. So how is the setup of this competition? So the setup of this competition is really similar to the setup in many machine learning competitions. So we have a data source, and the data source in this case are a number of images of knees and corresponding measurements. And then the challenge organizers split this data set into a training set. And then on the training set, we train our model if we have a neural network, or we tune our model if we have a one minimization, right? We still have one parameter that we have to tune. And in the case of untrained networks, we also tune our model because there are some hyperparameters to these models. So we either train or tune based on the training set, and then we get some model. And then we test that model on the training set. And then we evaluate our performance in some metric, for example, SSIM or signal to noise ratio, and then we get those numbers just as an example for one method. So now if we want to use our methods in practice, there is, however, the concern that this kind of setup might not reflect the performance in practice. In particular, in practice, there are robustness concerns. So there are really at least 3 robustness concerns. So the first robustness concern is that the neural networks might not be stable with respect to adversarial examples. So the idea here is not that there's an adversary in an MRI scanner, but the idea is that there might be some failure in the system, some small failure, some technical failure, and that failure could generate some worst case perturbation. And the worry is that this worst case perturbation can have a very large effect. The second concern, and that's a very valid concern, is that there is a distribution shift, in the sense that we saw that in the competition, the training data and the test data are really taken from the same distribution. So that's not really the case in practice, because in practice we train on data from, for example, one hospital, and then we apply our method to the data from another hospital. So there is a shift in the distribution. And if there's a shift in the distribution, that can potentially deteriorate the performance of our methods. The third concern is that our method might not be able to recover fine details. So here's an example that I took from the paper by Knoll et al. And they were showing one example from the FastMI competition, and this example shows an original image, and it shows the reconstruction obtained by the deep learning method, or by the best deep learning method in this case. And what we can see here is in the original image, there is a pathology, and then the reconstruction, the pathology is completely gone. So in this case, this could have changed the diagnosis, because the diagnosis relies on detecting this pathology. So in this case, what we really want to do at the end is make a diagnosis based on these images, and if whatever method we use changes the image and leaves out important part, that's of course concerning. So what we wanted to do in this work is we want to evaluate the robustness with respect to these 3 notions of robustness. And we want to evaluate the 3 classes of methods that we have just seen. So end-to-end neural networks, the classical sparsity-based methods, and the untrained neural networks. All right, so let's start with adversarial robustness. So adversarial robustness has been studied before, but let's first see what adversarial robustness is. So we have a reconstruction algorithm. So the reconstruction algorithm can be a deep neural network, or a one minimization, or the deep decoder. So those are the 3 conceptually different methods. An adversarial perturbation is the following. Psi applied to AX star gives us a reconstructed image. So now we are looking at, well, if we apply psi to AX star plus some perturbation that is chosen in the verse, that is chosen so that the difference between those 2 reconstructions is maximized. So that's what we define as an adversarial perturbation. So it's like a worst case perturbation, one that really makes our image as different as possible, and the perturbation is added to the measurement, right? So that's important. And it's limited in L2 norm in our case. Okay, so adversarial perturbations have been studied before by this paper that is relatively well known that appeared in PNAS. And this paper found very concerning news. So they found, and I'm quoting the paper here, deep learning typically yields unstable method for image reconstruction. And they also found that there are cases where deep learning attains lower errors than sparse regularization, but in doing so is unstable. So this paper really promoted this idea that, well, deep learning could be very unstable, and L1 minimization potentially could be more stable. So we looked into this. And what I also want to mention is these concerns are really taken serious by the community of radiologists. So here's an let's say newspaper that caters to radiologists, and they picked up this study and said, well, AI-based image reconstruction techniques could lead to misdiagnosis because of these adversarial perturbations. So these things are really taken serious, I think, these concerns. All right, so we looked at the adversarial robustness as well for these methods, and here's what we find. So let's first look at this experiment here. So what we see here is we generate different perturbations, or we generate perturbations of different strengths, epsilon, and we generate perturbations for the unit. So the reconstruction algorithm psi that you saw in the equation before, we took that as a unit. And then we evaluated, well, how much does it affect unit? And it affects unit quite a bit. And then we also looked, well, how much did the perturbation that we find for unit affect, for example, L1 minimization? And then it affects L1 minimization much less. And how much does it affect conf decoder and so on? Also, it affects conf decoder quite a bit less, right? And so if we only look at this image here, we might think that neural networks are unstable because the unit perturbations affects the unit most. And that's essentially the experiment that has been done in this previous paper. However, if we do the following, if we also look for L1 minimization perturbations, and then we check, well, how much do they affect L1 minimization, then we see, oh, they affect L1 minimization quite a bit, but they don't affect unit quite a bit. So if we would only look at this part here, at this simulation, then we would think that L1 minimization is actually stable, but then we would think that L1 minimization is not stable, but that the unit is stable. But if we take these two things together, then what we conclude is that, well, the perturbations are very specific for the respective methods. So L1 minimizations are bad for L1 minimization, unit perturbations are bad for the unit, but there's really not that much of a difference, at least from those perturbations, in terms of how bad are L1 minimizations for L1 versus how bad are unit perturbations to unit. And so we did that experiment, of course, also for the other methods. And from this whole experiment, we concluded that untrained networks seem to be as unstable as trained ones. So we couldn't really find a difference in terms of how unstable are untrained methods versus trained methods. However, we can also not give a definite answer to the question which one is more stable or which one is less stable, because when we find adversarial perturbations, we are not sure whether we find the most adversarial perturbations. Could be that there are more worst case perturbations. However, what this experiment really tells us is that right now, to the best of my knowledge, there is no evidence for deep networks being fundamentally less susceptible to adversarial perturbations in the context of MRI recovery. Okay, so the second notion of robustness we looked at is the robustness with respect to distribution shifts. So the first distribution shift we looked at is a dataset shift. So the dataset shift is as follows. Let's say we train our network on the fast MRI data. So from the fast MRI data, we have a training set and we have a test set, right? And then we imagine a situation where we train the method on the FastMI dataset, and FastMI dataset is collected from New York University, and then we apply it to a different dataset, in this case, a dataset that has been collected at Stanford. We call this a Stanford test set. There are differences on how these two datasets are collected. So, for example, the frequency resolution is different, the slice signal is different, so we have a lower SNR. So there is really a difference in how they were collected, but in both cases, those are knee images, right? So it is a reasonable, it's a reasonable shift to consider, and it's definitely a real world data set shift. Okay, so, and again, we're going to evaluate the different reconstruction methods, sparsity-based ones, untrained neural networks, and end-to-end networks. And for end-to-end networks, we consider the unit and the variation in it. So in order to give you some perspective on how to think about this problem, let's recall how many parameters there are. So for the sparsity-based methods, there's really just one parameter that we are tuning based on our training set, and that's the regularization parameter. So for the untrained neural network, there are a few more hyperparameters that we are tuning. In this case, it's like 5 hyperparameters that we are tuning based on our training distribution or on training data set. So these networks, or these methods, the sparsity-based and the untrained network, they are untrained, but they are tuned, right? So there might be like a slight dependence on the training distribution, but we don't expect it to be too much, because it's really just like one real number or 5 discrete numbers. In contrast to that, the end-to-end networks, the unit and the variation network, those are really large networks. So 50 million parameters, right? Whatever fits on your GPU, and all those parameters are learned. So there we would expect to have quite some dependence on the training distribution. So here's what at least I expected, or what we might expect, and that's a sketch. So what we're plotting here is we're plotting the structural similarity index metric. So it's a performance metric for images on FastMI, so larger is better. And we plot this versus the Stanford data. So if X is equal to Y, then there's no change. So for a one minimization and for the deep decoder, at least I expected that there's very little change, because they don't depend very much on the distribution. And we expect X to be equal to Y in the case where both the FastMI data set is as difficult as the Stanford data set. And a reasonable assumption is to say, well, it could be that these two test sets are similar to reconstruct, because both are knee images, so they should have a similar level of fine details and so on. What I also expected is that the varnet and the unet, that they perform worse, because we train on one distribution, and maybe the network really picks up on that distribution. So it is reasonable to believe that the methods that are actually trained are susceptible to this distribution shift, and the methods that are only tuned on the data are not so susceptible to the distribution shift. So that's one possible outcome. Another possible outcome is that everything shifts by a little bit, but unet and varnet shift more. And that's a plausible outcome, because it could be that the Stanford data set just contains more difficult to reconstruct examples, right? It could be that those are images that have more fine details, and so they are just more difficult to reconstruct. And then the absolute numbers for a one minimization and the decoder would be also smaller. But again, in this case, I also expected unet and varnet to be more susceptible to the shift, just because they have 50 million parameters, so they're really trained on or they should really depend on the training distribution. But what ends up happening is the following. So here are the actual numbers for the dataset shift. What we see here is we tested this for different variations of the varnet. So we just looked at large varnets and small varnets. Same for unet. Each of these points corresponds to a different configuration, to a larger unit and to a smaller unit. So just different units. And the blue ones and the green ones, those are different versions of the one minimization and different versions of the untrained neural networks. For example, for a one minimization, right, we could impose wavelet sparsity, we could impose total variation as a sparsity. So just different variations of the same thing. And so what we see here, what I found surprising is that the untrained networks or the untrained methods, they are even more susceptible in this case, or slightly more susceptible to the distribution shift in this particular example. So here the loss in performance for the blue points is even more than for the black points, right? And the loss in performance for the green point is also slightly more than for the red points here. So even so, the untrained methods are only tuned on the distribution, they really suffer quite a bit also under the distribution shift. And then the best performing network, so the VARNet, doesn't suffer more under this distribution shift than the untrained networks, right? Even so, it has these 50 million parameters. Okay, and so this finding is something that we could replicate for a number of different distribution shifts as well, right? Because now you could say, well, that might be something that's very specific to this particular distribution shift, but it turns out that we see a very similar behavior also for other distribution shifts. So here's another distribution shift. So that's an anatomy shift that's not as likely to occur in practice because we know whether we scan a knee or a brain. But the anatomy shift is as follows. We train on brain images, and then we test on brain images, and we plot this versus testing on knee images. And again, here's the line y is equal to x, and what we see here is that again, like all methods are affected by this distribution shift. And again, we can see that there's a very strong correlation between the in-distribution performance and the out-of-distribution performance. And that holds true both for the methods that are really trained on a lot of data and the methods that are only tuned on a little bit of data. Okay, and what we can also see from this experiment is that the distribution shifts, they really mess with our performance quite a bit. So here you can see reconstructions for L1 minimization. So you see there are visible artifacts if we reconstruct a brain. And if we look at the untrained methods, they get just very smooth. So you don't see that so well, perhaps, but they really omit some details. And UNet and VARNet, they also have these visible artifacts under distribution shifts. So distribution shifts are really a problem for those methods, but for all methods, not only for the deep networks, also for the untrained networks like L1 minimization. Okay, so here's another distribution shift. So that's called an adversarially filtered shift. So here we took the fast MRI data and we looked at particularly difficult to reconstruct examples. So that's fast MRI adversarial. And as you can see here, again, there's this very strong correlation between in-distribution performance and out-of-distribution performance. And also, again, all methods are affected by this distribution shift, not just the ones that are like trained, also the ones that are tuned on the data. All right, and I want to mention here like a really nice work from Taori, Ludwig Schmidt, and so on. It's called Measuring Robustness to Natural Distribution Shift in Image Classification. And so they looked a lot on image classification problems, and they looked at, well, how do natural distribution shifts in image classification affect the performance? And of course, image classification and image reconstruction are two quite different problems, but they identified that there's this very strong correlation between in-distribution performance and out-of-distribution performance. So that's one finding. And the other finding that they had is that natural distribution shifts are actually quite difficult to address. So the brown points correspond to robustness interventions, like algorithmic ideas, how to deal with distribution shifts. And as you can see here, they didn't, they don't seem to help very much. And the green points correspond to training on much more data. And it can be seen that this sometimes helps a little bit against these distribution shifts, but it also doesn't seem to completely solve those distribution shifts. So they concluded that natural distribution shifts are an open research problem, so they are difficult to address. So again, image classification and image recovery are different problems, but those results indicate that it could be potentially difficult to address the distribution shifts also in image recovery. All right, so now let's talk about the last notion of robustness, and that's recovery of small features. So the motivation to look at recovery of small features is this plot by the paper in Knoll et al. So remember, there's this pathology, this small point, and the deep learning-based methods didn't recover this pathology well, right? They didn't recover this pathology, and here the concern really is that deep network-based methods might fantasize something, right? So they might fantasize away these pathologies. So in order to test this hypothesis, what we did is we looked at real-world pathologies, a lot of real-world pathologies, and we looked at, well, how well does the method, or do the different methods recover only this real-world pathology in the image versus how well does it perform on some image metric on the entire image. And what we found is that the error in recovering the pathology is almost perfectly linearly correlated with the ability or with the overall reconstruction error, right? So that's not super surprising, because you would expect fine detail recovery to be correlated with with like recovery of with overall recovery performance, and that's indeed the case. So in this case, the network that gives the best performance in overall reconstruction error also gives the best performance in recovering these pathologies. And the one minimization, which has the worst reconstruction error, also performs worst in recovering these pathologies. So again, in this case, like if you want to recover pathology, it still seems that your best hope seems to be the variational network, or the best network, or the best neural network in this case. Okay, so here are the conclusions. We looked at 3 different notions of robustness. The first one are adversarial perturbations, and for adversarial perturbations, we really found no evidence that deep neural networks are fundamentally more susceptible to adversarial perturbations in sparsity-based method or other untrained networks. For distribution shifts, we found that there's a very strong linear correlation of in-distribution and out-of-distribution generalization. So the methods that perform best in distribution, they also perform best on the out-of-distribution examples. With regards to recovery of fine details, we found that this is strongly correlated with overall reconstruction quality. So again, if a method performs best in terms of overall reconstruction quality, then it also performs best in recovering fine details. So from those 3 findings, we conclude that accuracy is actually a good measure for performance. So overall reconstruction quality measured by some metric like structural similarity metrics is actually a good measure for the performance, also for out-of-distribution data and for the recovery of fine details. What we also find is that the frontier for really getting better models in practice is to find models that perform better under distribution shift, because it is under distribution shifts, this really messed up the performance of models, right? As we see, of all models, even untrained ones. And so that could be a real problem. And in order, to really make progress for this problem, something important to look at are distribution shifts. Okay, so here are a few references. So the paper that I talked about is measuring robustness in deep learning-based compressed sampling. It appears at ICML this year. Here's code to reproduce our results. Here are 2 papers on the untrained neural networks, and here's a paper by the Berkeley group on on natural distribution shift and image classification that I highly recommend to look at. All right, so thank you for your attention.